Hi, welcome back. Welcome to all. Now I'm welcoming you all to Unacademy, India's largest online learning platform. Now Unacademy is going to providing the coaching for GATE and engineering service examinations with the top faculty. About myself, I G Venkata. I have 16 plus years of teaching experience, and so far I mentored more than 60,000 plus students for their GATE examination. At present, I am doing my PhD in JNTU Kakinada, and my specialization is VLSI design. First, we check how to get the Unacademy learning app in your device. Okay, if this app is in your device, it's okay. Otherwise, just open the Play Store. In that, type Unacademy. Once you type Unacademy on that, you get the Unacademy learning app like this. Okay, now just click on this install button. By clicking on this install button, it will install the Unacademy learning app in your device. Once you open that device, once you open that Unacademy learning app, you will get what are the different courses available and who are the top faculty handling the subjects in that each course. Okay, you get that, and brief introduction about that faculty also you will get. From that you can estimate, okay, your classes are taken by which faculty. Now here are few of the top educators. Ankit Goyal sir, he is the 2 times All India GATE topper in electrical stream, and Tiwari sir, he is the IIT topper, and Jain sir, he is the top faculty from computer science, and Jaspal Singh sir, he is the ex-IAS officer. And here are some other faculties from different departments. Now, so I am happy to say that we are going to launching 2 new batches. For one is for GATE 2022, other one is for GATE 2023. This is Ascend batch for GATE 2023 mechanical engineering. This is going to start from 8th February 2021. 8th February 2021. Don't forget the date. If any of your friends are in mechanical engineering stream, please inform this one to them. And there is a evolve batch for GATE 2022. This is for same mechanical engineering, and this is also going to start from 8th February 2021. So these are the top faculty who are handling the classes in that. Next, there is Ascend batch. Again, this is for GATE 2023. Now this time this is civil engineering department. This is also going to start from 8th February. 8th February. Okay, and here are the top faculty who are handling your classes. Okay, and don't forget to use my code during subscription VROW10 to get 10% discount. To get 10% discount. Okay. To get 10% discount. And again there is a evolve batch for civil engineering. This is for GATE 2022, and this is also going to start from 8th February. Here are the top faculty who are handling the classes of civil engineering subjects. Don't forget to use my code VROW10 during subscription to get 10% discount. Okay. Now again there is a evolve batch. This time this is for computer science and information technology. This is for GATE 2022. Now don't forget to use my code VROW10 during subscription, and this batch also going to start from 8th of February. 8th of February. So next one is Ascend batch for GATE 2023. This is for electrical engineering. This batch started from 1st February 2021. Here are the top faculty who are handling the classes. Don't forget to use my code VROW10 during subscription to get 10% discount. Next one is, there is a Ascend batch for Electronics and Communication Engineering. Ascend batch for Electronics and Communication Engineering. Here are the top faculty who are handling the classes here. And this batch started from 1st February 2021. Okay. Next, again there is electrical department. This is Eval batch for GATE 2022. Okay. This is going to start from 1st February 2021. So here are the top faculty who are handling the subjects in this. Okay. So don't forget to use my code VROW10 during subscription to get 10% discount. To get 10% discount, don't forget to use my code. Just use my code VROW10, then you get 10% discount. And again, we back to Electronics and Communication Engineering. This is for GATE 2022. It is the Eval batch. Okay, here are the top educators who are handling the subjects in this. Okay, now this batch starting from 1st February 2021. Next, we are moving to chemical engineering. So chemical engineering students, if any is there, anybody is there, you must thank to Unacademy. Outside, it is very difficult to get the chemical engineering faculty for training, provided trainings to students. So they gathered the top faculties from India in chemical engineering. They are providing the classes to you. So you must thank to Unacademy for this. So here are the top faculty who are taking the classes for chemical engineering students. This batch started from 25th January 2021. If any of your friends are from chemical engineering department, please inform this one to them. So now we check what are the different disciplines available in Unacademy for engineering and engineering services and GATE examination. Now mechanical engineering, electrical, civil, production and industrial, instrumentation engineering, chemical engineering, and electronics and communication engineering. These are the different disciplines available. Now there are two types of subscriptions. Plus subscription and iconic subscription. Plus subscription is the basic subscription. Iconic subscription is the next level of the subscription. Okay. To get a success, what we have to do? First of all, I want to success in exam. For that, what I want to do? See, first one is I want to prepare well. After that, I have to write more number of exams. Once exam is completed, I have to analyze that paper. What is the proper solution for that, and what is the solution I done for that? And after that, whatever the mistakes I done in that exam, I have to note down those mistakes. In next level, I have to take care about not to repeat those mistakes. And from exam to exam, I have to assess the subject wise my performance, and from that I can understand, I can get where I am strong and where I want more preparation. Okay, now I concentrate on that subjects more. If I do analysis like this for a 1 year of period of time, then finally at the time of examination, I'm not possible to do any mistakes, because already we analyzed the mistakes what we done and we taken care, and we have some experience in that. Okay, see, for myself, I am do this one, move this one from here to there. Once you are moving that one from one point to another point, then you will face some problems in that moment. Okay, that is the practical one. So what are the obstacles you are getting during that moment? You need to clear that obstacles. Same way, during writing the examination, they given one problem. I want to get the answer. Okay, during simplification, I done a mistake. Instead of taking 10 power 20, I taken 10 power 18. Then total value will change. Okay, so that type of problems you are analyzed already before going to the examination itself. Okay, so once you analyzed all this, no chance of doing similar type of mistakes in the examination. So once you are not doing any mistake in the examination, so definitely you will crack your examination. Okay, so for that you may ask one thing, sir, we are busy with regularly we are busy with our college work, our semester examinations, semester classwork is going regularly, semester exams are there, labs are there, records are there, observations are there, what we have to do? See, for a student it is a difficult during his study in third year and final year. For a student it is a difficult to do this type of analysis, just they concentrate only on preparation. For that, you don't worry, we will take care of that. We will take care of that. Okay, in this iconic plan, we will assign a personal coach to you. For every student, we will assign a personal coach. The duty of this coach is regularly contact with the students. Okay, take the reports from the students, his progress report. He has to prepare the progress report, has to conduct the examinations to that student, and after examinations they have to analyze that exam, personal test what they've written, they have to analyze that exam. After analysis they have to report where student is good and where students are doing mistakes. Okay, where which topic students has to do more preparation, so that information they will provide. So we are taking care of their work, that one. For that we are assigning a personal coach to you. This is the highlight topic, highlight point in your iconic batch. This facility is for iconic subscription, and the remaining things are your classes are taken care by the India's best educators. There are interactive live classes. Okay, and structured courses and PDFs are available. Structured courses and PDFs are available. Next, live tests and quizzes. Live tests and quizzes are there. Now here personal test analysis is there, proper study planner they will prepare to you. Okay, you follow that, and study material also they will prepare to you. By following these two properly, you get, definitely you will success in your examinations, because you are not doing any mistakes. Okay, and already you analyzed where you are strong and where you are weak. Once you feel at this area I am strong, once I am feeling that I am strong in analog electronics, ADC, okay, and digital electronics, in examination first I attempt those questions only, because I am very strong in that. Okay, less time is sufficient to me to complete that, and after that we go to the remaining topics. Okay, so that work. So by doing these things, by following these things, definitely you will get success in your life, in your career also. Okay, now plus subscription is just a basic subscription, basic plan it is. Okay, so this is iconic. Here they will provide a personal coach to you. And one more thing, no need to move anywhere, just by sitting at your home itself you can get all these things. Personal eye to eye contact in through online. Okay, in your system you are there, and your personal coach is in another system. He is going to contact you personally. Okay, and after taking the report, he will forward that report to the respective faculty, and respective faculty will come and he will solve your doubts in that respective subject. Okay, so that are the benefits you are getting from iconic subscription. Now we check the costs of this. Costs are reasonable costs, are not that much heavy. If you observe one thing, see, these are the subscriptions we have: 1 month subscription, 3 months, 6 months, 1 year, like this. And the cost of 12-month subscription for plus subscription is, it is a plus plan is 30,250. After using my code VROW10 during subscription, after using my code VROW10 during subscription, you get that by 10% discount, that is 27,225. You can get it by 27,225. Okay, for that amount you get it. Clear? Now, if you compare this cost with your travel expenditure to take a coaching or to attend classes somewhere at outstation, your travel expenditure throughout that year is more or less 20,000 plus. Now, just by adding a little bit amount to this, you can, by sitting at your home itself, you can get the benefits. What are the benefits you are getting by attending the classes? More than that benefits you can get by sitting at your home itself. Okay, that is about your plus plan. Next one is iconic. This is very, very important. Okay, my suggestion is, if everything supports for a student in all aspects, try to give first priority to iconic. This is for third year students and this is for second year students. Okay, for a third year students, so for 1 year subscription it is 50,250 rupees. After discount, by using my code VROW10, you get a 10% discount. After that it became 45,225 rupees only. 45,225 rupees only. Okay, now this is the cost. Now this cost is more or less equal to the amount you are paying for a institute to take a GATE coaching, GATE classes. Okay, more or less equal to that. But here, in addition to that, you are getting more benefits. That is, first one is no need to move anywhere. By sitting at your home itself, you can get what are the benefits more than that. Second one is a personal coach is available. Once you done some work, that work is analyzed by the personal coach. Okay, and we provide a proper material to you. You can prepare that material. Okay, these are the external benefits you get, and more number of tests you are going to be writing, or more quizzes you are going to be attempting. After every test, okay, we are going to be analyzing your performance in that. So these are the benefits you get in iconic plan. Okay, next one. Okay, now we are moving to next topic in electronics and EDC. So already we completed up to some part. We done problems on mass action law. Now we are moving to energy levels. So this is the problem last class we completed. Now I am moving to next topic. Calculation of intrinsic Fermi energy level. Already last class we completed the calculation of Ni we completed. Now we are going to calculating the EFI, intrinsic Fermi energy level. EFI we are going to calculating. Okay, now, so you are saying it is an intrinsic semiconductor. Once it is intrinsic semiconductor, we know about electron concentration and hole concentration. So N equals to P equals to Ni. N equals to P equals to Ni, and EF is nothing but a EFI, intrinsic Fermi energy level. EF is EFI, intrinsic Fermi energy level. Now I am writing these two values, placing in the standard two equations what we have. So we defined already electron concentration and hole concentration in a semiconductor. That is, N is, we defined it as Nc into e power minus of Ec minus EFI by kT. Sorry, Ec minus EF by kT. Similarly, for P, whole concentration is Nv into e power minus of EF minus EV by kT. These are the equations. Now once it is intrinsic semiconductor, we can replace this N by Ni, because electron concentration equals to intrinsic carrier concentration in intrinsic semiconductor, and this whole concentration you can replace it by Ni similarly. And EF Fermi energy level I am replacing it by EFI. Similarly here also EF replacing by EFI. Now these two, this is Ni you are saying, and this is also Ni. So both are equal. Just I am equating both. Okay, by equating, taking this Nv this side, therefore Nc by Nv is here Nc by Nv. Now this one is e power minus EFI minus into minus plus EV. Taking this one this side, now it is e power plus EC minus EFI by kT. Now minus EFI, that is minus 2 EFI. Now I'm taking both sides a natural log. Once by taking natural log on both sides, we can write EC plus EV minus 2 EFI by kT equals to ln of Nc by Nv. Now whatever the kT you have, just take that kT and place here. From that I am defining EFI. So finally you can get EFI is intrinsic Fermi energy level. EFI is EC plus EV by 2 after simplification. EC plus EV by 2 is the midpoint of the energy gap minus kT by 2 into ln of Nc by Nv. And if you take your energy band diagram like this, it is EC and here it is EV. It is EV. So midpoint of that one is this one. So we can write this midpoint is EC plus EV by 2. EC plus EV by 2. That is the midpoint. But this is your energy gap. It is your energy gap. And this is midpoint in this sense. You can write this one, and this one value is Eg by 2. Energy gap by 2. So you can also write intrinsic Fermi energy level is energy gap by 2 minus kT by 2 into ln of Nc by Nv. Nc by Nv. That is the intrinsic Fermi energy level. Okay, equation for intrinsic Fermi energy level. Now we are going to calculate the Fermi energy level of remaining semiconductors, N type and P type. So in this Nc and Nv, already we know the values of Nc and Nv. Just I am going to that NC by NV. Substituting the values of NC and NV. In NC and NV, all values are same except Mn star and Mp star. That's why it is Mn star by Mp star. Whole power 3 by 2. You can take this 3 by 2 this side. Then it is 3 by 4 into Kt ln of Mn star by Mp star. If the effective masses of these two Ln star and Mp star are equal, then it became 1. Now ln of 1 is 0. Okay. Now it became Fermi energy level is exactly at midpoint of the energy gap. Fermi energy level is exactly at midpoint of energy gap. Okay. Now, so I am going to relating different energy levels which are available in n-type semiconductor. See, this is the energy band diagram of a n-type semiconductor. This is the energy band diagram. EC, EV, EFN, intrinsic Fermi energy level of see, EC, maximum energy, minimum energy level of conduction band. EV, maximum energy level of valency band. Fermi energy level of n-type semiconductor, and intrinsic Fermi energy level. These are the different energies present in this. Now you need to relate all these one to another. Okay, for that I am going to take the basic equation. So our basic equation is, we know the value of n. N is Nc into e power minus of Ec minus Ef by Kt. Minus of e power minus of Ec minus Ef by Kt. We know that. And for intrinsic material, n equals to Ni and Ef equals to EFi. Substituting these two values in this expression. So Ni is Nc into e power minus of Ec minus Efi by Kt. Let us take it as equation number 1. Okay, so that means your Ni value is Nc into e power minus of Ec minus Efi by Kt. Just take this one this side, Ni this side. Therefore, you get after simplification Ec equals to, okay, sorry, it is EFI. Okay. We need to get, already this part is completed. Now I want EC and EFN. First of all, EC and EFN, I am going to relating these two. Now, from this, it is EC. And next, EFN means it is a n-type semiconductor Fermi energy level. For n-type, we can write n equals to nd and Ef equals to, for n-type you can write Ef equals to EFN. Ef equals to EFN. Substitute these two in this expression. So now nd equals to, electron concentration is n0. So n is n0 under steady state, which is approximately equals to doping nd equals to Nc into e power minus of Ec minus EFN by Kt. Okay, Ec minus Efi by Kt, and here it is Ec minus Efn by Kt. Let us take equation number 1 and it is equation number 2. Now divide one after another. Okay, sir. Now I am going to taking this 1 by 2. So 1 by 2. So in 1 by 2, you get Ni by Nd. Ni by Nd or N0 you can take. Ni by N0. Later we place that N0 by Nd. Nc by Nc both will cancel, and e power this one by this one. So e power minus Ec plus Efi Efi plus Ec minus Efn by Kt. So in this, minus EC plus EC gets cancelled. From this we can write EF n is more above the EFI, therefore EFN minus EFI can write KT into ln of n naught by ni, n naught by ni, or EFN minus EFI is KT into ln of n naught is nothing but nd by ni. This is one equation related EFN and EFI. Now for EC and EFI, just this equation is sufficient for that. From this directly you can write, take this one this side, ni this side, then you can write EC minus EF, sorry, from this second equation, from this you can write EC minus EFN is KT into ln of NC by ND or N naught. That is the expression what we have. Okay, like this, whatever the energy, different energy levels we have in n-type semiconductor, they are related here. So this is another one, EFN minus EFI, KT into ln of ND by Ni. Similarly, I am moving to p-type semiconductor. The same way, whatever the procedure you followed previous case, follow the same procedure, then you get, this is your complete energy band diagram for a p-type semiconductor. EC at mid approximately EFI, this is EV, and here it is EFP. So first I am going to relating EFI minus EFP. EFI minus EFP. EFI minus EFP equals to KT into ln of P naught by Ni. Okay, or KT into ln of, in a p-type semiconductor, P naught is Na by Ni. That is the first expression. Second one is EFP and EV. So that EFP minus EV is KT into ln of NV by P naught, or KT into, or KT into ln of NV by P naught is nothing but a NA. This is the second equation. So by following the procedure what we applied in n-type semiconductor, here also we are following same thing. By following those things you get these expressions. So these equations are very useful to you in problem solving. Next, this is about your p-type semiconductor energy band diagram. Finally, whatever the expressions there I get in n-type and from p-type, I placed all the expressions at one point. This is for n-type, from n-type, and these are from p-type. Okay, please note down these equations. They are useful to you in problems. Now, see here we are going to doing some problems on this. See, silicon is doped with boron to a concentration of 10 power 17 atoms per centimeter cube. See, silicon is doped with boron. So boron is third group element, so it means they given Na 4 into 10 power 17 per centimeter cube. Per centimeter cube. Assume that Ni of silicon is 1.5 into 10 power 10. So they given Ni value of silicon 1.5 into 10 power 10 per centimeter cube. Fine. So and kT by Q 25 milli electron volts. It's okay. Vt is kT by Q. Compared to undoped silicon, undoped means it is intrinsic silicon, the Fermi level of doped silicon. So EFI minus EF doped silicon, it is they added boron. Okay, so they want EFP is how much compared to this, what is the value of this, where it is. We have a direct equation for this. That equation is EFI minus EFP is KT into ln of Na by Ni. Okay, this is nothing but a approximate whole concentration. Now just substitute the values. They given KT by Q 25 millivolts. KT by Q is 25 millivolts. It means KT is 25 milli electron volts. Take this one, substitute here. KT is 25 milli, 0.025 milli into ln of Na is 4 into 10 power 17 by Ni 1.5 into 10 power 10. So now it is 0.025 into, see, ln of 4 by 4 divided by 1.5, that is 2.66. So ln of 2.66 into 10 power 7 per centimeter cube. Okay, in electron volts total value. Now 0.025 into, you can write it as ln of 2.66 plus ln of 10 power 7. Sir, from next problem onwards I am going to simplify this one directly. I will simplify this. Now procedure I am going to be showing here. Ln of 2.66 plus ln of 10 power 7. It is 0.025 into ln of 2.66, that is 0.978, plus ln of 10 power 7, 7 into ln of 10. So it is 0.025 into 0.978 plus 7 into ln of 10. Ln of 10 is, we know that it is 2.3 something. 2.302. Now just simplify this. Into 7 plus 0.978, it is 17.09 into 0.025, that is 0.427 electron volts. So compared to undoped silicon EFI, doped silicon Fermi energy level EFP is 0.427 electron volts, down, goes down by 0.427 electron volts. Now just go and check your options. See, it is goes down by 0.427 electron volts. That is the option. Now I want after doping the Fermi energy level, I want with respect to conduction band edge EC, and I want with respect to EV also. For that you need to draw the complete energy band diagram. Now I am going to complete energy band diagram. EC let us take EV. So intrinsic Fermi energy level is approximately midpoint of this. This is p-type semiconductor Fermi energy level. It was close to this EV. Now it is our EC, EFI, it is EFP, it is EV, and we know that this is 1.1 electron volt energy gap at 300 Kelvin, and this is half of it, 0.55 electron volts. Similarly this one also same, 0.55 electron volts. And just before we calculated EFI minus EFP, that is 0.427. 0.427. Now I want the position of this with respect to this and with respect to this. With respect to this, it is 0.55 plus 0.427, that is 0.977 electron volts. So Fermi energy level after doping, the Fermi energy level of semiconductor is 0.977 electron volts down by EC, and above EV it is 0.55 minus 0.427. 0.55 minus 0.427, that is 0.123 electron volts. 0.123 electron volts. Okay, so by writing the complete energy band diagram like this, you can represent the whatever the value they want. Okay, now before doping this is the Fermi energy level, after doping this is the Fermi energy level. Now the position of Fermi energy level with respect to EC is this much, with respect to EV is this much, with respect to EFI is this much. So all possibilities we calculated. Okay, like that, once they given some data, based on that few part of data, you have to represent complete energy band diagram. Okay, complete energy band diagram, and from that what they want, you can provide that data easily from that. Okay, now I am moving to next one. An n-type silicon wafer has been doped uniformly 10 power 15 phosphorus atoms per centimeter cube. So phosphorus means it is Nd, 10 power 15 per centimeter cube. Calculate the position of the Fermi energy with respect to the intrinsic Fermi energy level, and T is 300 Kelvin and Ni is 10 power 10. So with respect to EFI, what is the position? Okay, now we know the equation. That means you need to relate EFI and EFN. You need to relate this. We have an equation for this, that is EFN minus EFI. But compared to EFN, EFI is below. EFI is KT into ln of Nd or N0 by Ni. So it is KT 0.025 into ln of Nd by Ni. Nd 10 power 15 by Ni 10 power 10 is 0.025 into ln of 10 power 5. So it is 0.025 into 5 into ln of 10 is 2.3 electron volts. Just simplify this. 2.3. It is 0.287 electron volts. 0.287 electron volts. Okay, so like that you can solve the problem. So based on this, the previous way how you completed the complete energy band diagram, you can draw like that also, because it is a silicon semiconductor. Temperature is at 300 Kelvin. Okay, so now I am going to that. EFI. Now the amount of doping what you done after that, this is the EFN. So it is EV, EC, EFI, EFN. So EFN minus EFI is, this value is 0.287. But we know the value of this 0.55 electron volts. This one also same. Now plus 0.55. 0.8375. Now with respect to this, with respect to EC is 0.8375 electron volts. Okay, and with respect to EV, its position is 0.55 minus 0.287, that is 0.263 electron volt. Now your Fermi energy level position is here. With respect to EV, it is 0.283 electron volts down. With respect to EFI, 0.2887 electron volts up or above. And with respect to EC, this is EV, sir, sorry, it is EC. With respect to EC, 0.263 electron volts below. With respect to EFI, 0.287 electron volts above. With respect to EV, 0.8375 electron volts above, up. Okay, so like that, once they given a small information to you, from that you have to complete the complete energy band diagram of your semiconductor. Next, see this. An intrinsic germanium wafer is doped with a shallow acceptor density of 3 Ni by 2. That means they given Na values are, acceptor density is 3 Ni by 2, where Ni is the intrinsic carrier concentration. At room temperature, all acceptors ionize. Calculate the hole density. What is the hole concentration? See, you observed or not, this is compared to Ni, it is just 1.5 times more, not much greater. Now you need to go for approximate exact model. So once it is Na, that is p-type semiconductor. So it is a p-type semiconductor. Now the exact equation for P0 is Na by 2 plus square root of Na by 2 whole square plus Ni square Na by 2 whole square plus Ni square. Just substitute the values. Na they given 3 Ni by 2, 3 Ni by 2 by 2, this 2, this one, plus square root of Na by 2 whole square. This is Na by 2, square of this 3 Ni by 2 into 2 whole square plus Ni square. Now it is 3 Ni by 4 plus square root of 9 Ni square by 4 square 16. 16 plus Ni square. So now it is 3 Ni by 4 plus square root of 25 Ni square by 16. Its value is 3 Ni by 4 plus 25 Ni square by 16. Square root is 5 Ni by 4. So it is 3 plus 5, 8 Ni by 4, it is 2 Ni. So whole concentration is 2 Ni, 2 times Ni. That is the whole concentration. Just I followed the exact equation, because to apply approximate, Ni is not that much greater compared to doping. Sorry, doping is not that much greater compared to Ni. So next one is, see, an intrinsic silicon wafer with 5 into 10 power 16 per centimeter cube phosphorus atoms and 6 into 10 power 16 boron atoms. So it is a silicon semiconductor of intrinsic doped with phosphorus. Phosphorus means Nd is 5 into 10 power 16 per centimeter cube, and Na boron, Na is 6 into 10 power 16 per centimeter cube, and Ni they given 10 power 10. All the dopants are ionized. What is the location of Fermi level with respect to the conduction band edge? First of all, you need to identify, you need to finalize the given semiconductor belongs to which type. See, the given semiconductor is in this Na is greater than Nd. Na is greater than Nd. So once it is the case, now it is a p-type semiconductor. Once it is a p-type semiconductor, the P0 is net doping Na minus Nd. Why? Because, okay, first get the net doping, later we finalize the P0. Now net doping is 6 into 10 power 16 minus 5 into 10 power 16. It is 6 minus 5 is 1, 1 into 10 power 16. So it is 10 power 16 per centimeter cube. 10 power 16 per centimeter cube. That is the net doping. And this net doping is much greater than Ni. Ni is 10 power 10. Compared to 10 power 10, it is 10 power 6 times more. 10 lakhs times more. Therefore, Na minus Nd is much greater than Ni. Therefore, you can take under steady state whole concentration is approximately Na minus Nd net doping, that is 10 power 6, 10 power 16 per centimeter cube. Now you know the Ni value and amount of whole concentration in a semiconductor of p-type. Now from this you can write an expression to relate Fermi energy level of intrinsic and Fermi energy level of p-type. Now that expression is EFI minus EFP is KT into ln of P naught by Ni. This is our expression. Now I am substituting the values in this. KT 0.025 into ln of P naught 10 power 16 by Ni 10 power 10. Now it is 0.025 into ln of 10 power 6. Now the 10 power 6 is written as 6 into ln of 10. Ln of 10 is 2.302. So now it is 6 into 2.3 into 0.025. That is 345. 0.345 electron volts. Now I am going to complete energy band diagram. Intrinsic Fermi energy level, and they given it is a p type, so p type Fermi energy level is somewhere here, that is 0.345, somewhere here. Now this is EC, EV, EV, EFI, it is EFN, EFP, p-type semiconductor. Just before we calculated, EFI minus EFP is 0.345. 0.345 electron volts. But we know that this is 0.55 electron volts and this is also 0.55 electron volts. Now with respect to this, it is 0.55 plus 0.345. That is 0.895, 0.895 electron volts, 0.895 electron volts, and with respect to this it is 0.55 minus 0.345. 0.205 electron volts. 0.205 electron volts. Okay, this is the complete energy band diagram. Now after doping, this is compensation doping, compensate doping, because two dopings they given, Na and Nd they given. Finally, with respect the Fermi energy level of a new material is with respect to EC 0.895 electron volts below, with respect to EFI 0.345 electron volts below, with respect to EV it is 0.205 electron volts above. These are the values. Okay, next, see, next one is calculate the Fermi level position in an n-type silicon sample with an electrical conductivity. They given a problem on conductivity. So far we did not complete it, but we know the equation for conductivity. I am going to using that. It's okay. And use the following information. Ni is 10 power 10 and mu n is this much, mu p is this much, and T is 300 Kelvin. Take band gap 1.1 electron volt. Okay, see, this is basically n-type semiconductor. First of all, n-type semiconductor, they given conductivity 1 ohm inverse centimeter inverse. So conductivity of n-type semiconductor is n naught into q into mu n. That is the equation. They given it as 1. From this I am going to calculating n naught value. It is 1 by q into mu n. So 1 by Q value is 1.6 into 10 power minus 19 coulombs into mu n 1350 1350 1350. Okay, and by simplification it is, so divided by 1.6 divided by 135, that is 4.62 into 10 power minus 2 into 10 power 19, that is the per centimeter electron concentration. So which is 4.62 into 10 power 17 per centimeter cube, that is the electron concentration. Now you need Fermi level position with respect to valency band maximum. So we know the Ni value as well as N0 value. Now I am going to calculating first Fermi energy level with respect to amount of EFI. So this is N type. So EF N minus EFI is KT into ln of N0 by Ni. KT 0.025 into ln of N0. So the N0 what we calculate is 4.62 into 10 power 17 divided by Ni. Just check the value of Ni what they given. It is 10 power 10. 10 power 10. Now it is 0.025 into ln of ln of 4.62 plus 10 power 17 by 10 power 10, it is 10 power 7, so 7 into ln of 10, so that is 0.025 into ln of 4.62. It is 1.5 plus 7 into ln of 10 is 2.302. Just simplify. 1.53, 7 into 2.3 plus 1.5, 17.6 into 0.025, so that is 0.44, so 0.44 electron volts. That is the with respect to intrinsic. Now I am going to writing the complete energy band diagram of it. This is EFI at center midpoint, and this is clearly they given it is a p type. Now it is close to this. Now this is EC, EFI, EFP, this is EV, and they given already this is 1.55, 0.55 electron volts, because energy gap they given 1.1 electron volt. Similarly this is also 0.55, and just before we calculated EF sorry, it is a n type, sir. Sorry, they are given n type. EFN minus EFI is a 0.44. So somewhere here we have EFN, and this value is 0.44 electron volt, and it became 0.11 electron volt, and with respect to valency band it is 0.55 plus 0.44, 0.99 electron volt, 0.99 electron volt. Now see the option what they want. They want Fermi level position with respect to valency band maximum with respect to EV. So with respect to EV, position is EFN is 0.99 electron volts. Just take the closest value. So this is the closest one, 0.89 or approximately 0.9. Okay, that is the closest value. So like that, by they given, instead of giving the concentration directly, they given concentration in terms of conductivity. Okay, first we have to calculate the conductivity from the conduction. So already we completed this. Now NC and V. Okay, next we move to current densities. After current densities we solve that problems. See, so far what you know is, once you have a semiconductor, you know how to control the carrier concentrations in that semiconductor. Okay, carrier concentrations. So that means by increasing amount of doping, majority carrier concentrations can be increased and minority carrier concentration is going to decrease. And by increasing temperature, majority will increase as well as minority also increase. But the percentage of increment in minority charge carriers is very high compared to percentage of increment in majority carrier concentration. That's why to increase the minority carrier concentration in a semiconductor, so increasing temperature is the best process. Okay, so after that we concluded, anyway carrier concentration is under your control. That's it. Once carrier concentration is under your control, so by providing a proper movement in the carriers, you can get current through that. By providing a proper movement of carriers, you can get a current. Okay, now here we have two types of current densities. First one is a drift current density, second one is diffusion current density. That means here in semiconductors we are representing current in terms of current density, current per area. Current density is represented by the letter J. Current density is current by area. Current by area. We have two types of current densities, drift current density, second one is diffusion current density. What is drift current density? For example, I am going to taking a semiconductor. In this semiconductor we have plenty of charge carriers. Now this is subjected to an external potential like this. So that means this end it became positive and at this end it became negative. This end it became positive and at this end it became negative. Okay, once it is positive, this side became positive and this side became negative. Now an electric field is directed away from positive and towards negative. Due to this, if you take any electron here, it is attracted towards this. Now electron is moving in the direction opposite to the direction of electric field. And if you take any hole here, that hole is moving in the direction of electric field. Now here the movement of charge carriers is by the application of electric field. So due to this electric field, your charge carriers are moving. So that is called drift current density. That is called drift current density. Okay. Next one is diffusion current density. In that case, let us, I am taking a semiconductor. In this, minority charge carrier concentration is constant throughout the region. Okay, diffusion current density. Most of the diffusion current density is due to minority charge carriers. Okay, now, so this is under steady state minority carrier concentration. Once this at this end, if I am going to place some light upon this, that means at one end it is illuminated by light. What happens is more number of charge carriers are generated because covalent bonds are breaking. At this end only covalent bonds are breaking, that's why more number of charge carriers at this end only. And if you observe, at this point more number of charge carriers, and at this point less number of charge carriers. Now there is a change in carrier concentration. There is a change in carrier concentration with respect to distance. This change in carrier concentration with respect to distance is called concentration gradient. Concentration gradient. Concentration gradient. Okay. So due to this concentration gradient, that means high concentration at one point, low concentration at another point, your carriers are moved from high concentration region to low concentration region. This movement is called diffusion movement. Diffusion movement, and this current is called diffusion current. Okay, in this movement is called a drift movement, and this current is called drift current. Drift current. Okay, sir. So drift current and diffusion current. So we define those two like that. Now first I am going to drift current density. Drift current density. Just take a note of this. Yeah, just 1 minute, please. Thank you. Now, here see this. Now we are going to drift current density. Here I am taking a conductor of cross-sectional area A, and length of the conductor is L, and total number of electrons in this conductor is N. N is the total number of electrons. Now that is subjected to external electric field. Here it is. This is positive and this is negative. Now electric field is directed in this side. Due to this electric field, electrons will move in the opposite direction. Electron movement is like this. Now electrons are moving in a direction of opposite to the electric field with a drift velocity, with a velocity of Vd. Now this movement is called drift movement, and the velocity at which your electrons are moving is called drift velocity. Vd is drift velocity. Drift velocity. Ed is drift velocity. Now with the velocity of Vd, they are traveling a distance of length L within a time of t. Now we can relate drift velocity is amount of length it traveled, distance they traveled by amount of time it taken. That is drift velocity. Now keep it outside. And we know the current, we need J drift current density we need to calculate. But it is nothing but a drift current by area. Now I drift can be written as Q by T, rate of flow of charges. But here number of electrons is N. So total current is N into Q by T. From this I am taking T value as L by drift velocity Vd. Take that and substitute that one here. Therefore we can write I drift as equals to I drift equals to N into Q by T. T is L by Vd. L by Vd. L by Vd. So which is N into Q by L into Vd. That is our expression for I drift. Take that one and substitute in J drift. So we know J drift value. We know J drift. J drift is I drift by area A. Drift by area. Now substituting I drift value here. Therefore it is N into Q into Vd by L by area A. Now it is number of electrons by length into area. It is volume into Q into Vd. Now length into area is nothing but a volume. Is volume. So in place of that, now length into area is volume. So therefore J drift can be written as this is a total number of electrons by volume into Q into Vd. That is N by volume is concentration of electrons N into Q into Vd that is the drift current density. So drift current density is N into Q into Vd. So and see, if you observe, let us take this is a positive plate and negative plate. So electric field is directed this side. Now due to that electric field, your electron is moving in this direction with drift velocity Vd. Electric field intensity is equals to E. For example, the applied voltage is V. V volts you are applying here and separated by a distance of D. This is the material. Now you can write the electric field intensity is V by D volt per centimeter. That is the units. Volt per centimeter. Now, see, Vd is drift velocity. If I am going to increasing the applied voltage, the speed of the electron is increasing. Once the strength of the electric field is varying, electron velocity also varies. That means whatever the drift velocity we have, the drift velocity is directly proportional to applied electric field. Now you can simplify that. Vd is some proportionality constant mu into applied electric field E. Some proportionality constant mu into applied electric field E. Now that Vd is written as mu into E. That mu is called mobility. For electrons, mobility is mu n, where mu n is electron mobility. That is the value of, that is the equation for drift velocity. Mu n is electron mobility. Similarly, we have mu p also. Mu p is called hole mobility, and practically mu n is greater than mu p. And one more thing, just take this one, substitute in that. The equation what we derived so far for drift current density is n into q into Vd. Now substituting the Vd value, mu n into E. So n into q into mu n into E. This is the drift current density equation. And in this, I am taking n into q into mu n. That n into q into mu n is the conductivity, sigma n or sigma. It is n into q into mu n is conductivity. Except E, remaining is conductivity. And 1 by conductivity is resistivity. Okay, at the same time, so n into q we called it as rho v, volume charge density. So there is a difference between rho and rho v. Rho is resistivity, rho v is volume charge density. Okay, now simply you can write, this is the expression for drift current density. Now if you take a semiconductor, in that we have electrons and holes both. Now total current density is current density by electrons and current density by hole. That's why I'm right. That's why I'm going to writing here. See this. Now similarly, hole drift current density can be written as P into Q into mu P into E. Total current density is J drift is N into Q into mu N into E plus P into Q into mu P into E. See, total current density, total drift current density is J drift by electrons plus J drift by hole, J drift by holes. Therefore J drift is electron current density, drift electron current density is N into Q into mu N into E. Similarly, hole drift current density is P into Q into mu P into E. Just I am taking Q common in that. Now it became Q into N into mu N plus P into mu P into applied electric field. This is the standard equation for drift current density. And by removing this E, except E, remaining is conductivity. So total conductivity is Q into N into mu N plus P into mu P. N into mu N plus P into mu P. So that is the conductivity value. Okay. So that is the equation for conductivity and current density, drift current density. Next one. So here we have different type of semiconductors, intrinsic, N type and P type. So you should be thorough with each and every type of semiconductor conductivity and current density. See, here I am representing that. First I am taking intrinsic semiconductor. For intrinsic semiconductor, N equals to P equals to Ni, we know that. And first of all, this is our standard equation for current density. J drift is Q into N into mu N plus P into mu P. This is the expression. Now for intrinsic, N equals to P equals to Ni, just substitute in place of N and P, substitute Ni. Now take that Ni common. So Q into Ni into mu N plus mu P into E. Except E, remaining is the conductivity. Q into Ni into mu N plus mu P. Now take N-type semiconductor. We know that in N-type semiconductor, N is approximately Nd and P is Ni square by Nd. We know that N is approximately amount of doping Nd and P is approximately, P is Ni square by Nd. Substitute that value. In place of N, I placed Nd. In place of P, I placed Ni square by Nd in above equation, in this expression. But compared to this Nd into mu N, this is much smaller value. We can neglect that. So Q into Nd into mu N into E, that is the conductivity approximate. So in that, whatever the E we have, just I am removing that E. By removing that E, it became Q into Nd into mu N. Q into Nd into mu N. That is the conductivity by N-type semiconductor. Similarly, I am taking P-type semiconductor. For P-type, Na, P is equals to Na, P equals to Na, N is Ni square by Na. Take that values of N and P, substitute in our standard equation. Now this is N, Ni square by Na and P is Na. But this is much greater than this, so we can neglect this. By neglecting that, so it became sigma P is Q into Na into mu P. Okay, that is conductivity. This is current density. So far we know the current densities and drift current densities and conductivity for each and every semiconductor. From that, what we observed, we calculated conductivity. So we know, let us take a semiconducting bar. Semiconducting bar I am going to be taking like this. Now the cross sectional area of this semiconductor is, let us take it as A, and length is L. Okay, now it has some conductivity. This conductivity is a function of either Ni value or amount of doping. By changing the amount of doping, conductivity is changing. Just before we mentioned resistivity is 1 by conductivity. Now see this. Resistance of this bar can be written as rho L by A. So rho is nothing but a 1 by conductivity. 1 by conductivity into A. That is A. For this specimen, length is constant and area is constant. Now conductivity is a function of doping, amount of impurity. By changing amount of impurity, rho is changing with respect to that resistance also going to be changed. See that by changing the amount of doping, the resistance of that conducting bar we are changing. Okay, by changing the amount of doping, we are going to changing the amount of resistance provided by that particular semiconductor. We are changing that. Clear? Next point. So this is the conductivity. Okay, next I want to get minimum conductivity. What is the minimum conductivity of a semiconductor? I want to know that. Okay, so for that, first I am taking the equation for conductivity. This is the conductivity equation. Sigma is Q into N into mu N plus P into mu P. This is the conductivity equation. So I want to get minimum conductivity. So for maximum conductivity, we can't say this is the maximum conductivity, because once amount of impurity is increasing or doping is changing, electron hole concentrations are changing, increasing, majority carrier electron concentration in n-type is increasing, now conductivity is increasing. So more doping, more conductivity. You can't say this is the maximum conductivity. But in case of minimum, there is a limitation. Because whatever the thing you can do in your semiconductor, your Ni value not less than something, N value. So I am going to applying that concept here. Now, to get the maximum or minimum value of a function, differentiation of that function with respect to that variable equal to 0. So by doing this, you get at what value of that particular variable that parameter is minimum. You get that one. Okay, so I am doing the same thing here. Here I am doing the same thing. See, this is the equation and we know that, but in this one problem, two variables N and P, these are the two variables. Only Q, mu N and mu P are the constants. Q, mu N and mu P are the constants. Okay, now N and P are the variables. Two variables. Now I am converting that one into single variable. From mass action law, we can write N into P equal to Ni square. Ni square. From this, we can take P value is Ni square by N, or you can take N value also, it's not an issue. Now substitute this P value in this. So it is Q into N into mu N plus Ni square by N into mu P. This one. Now I am differentiating this with respect to N. Now the d sigma by dN is, see, after substitution, this is the equation. After substitution, sigma is Q into N into mu N plus Ni square by N into mu P. That is the expression. Now I am going to d sigma by dN, which is Q constant, N dN by dN is 1 into mu N constant plus Ni square into mu P constant into differentiation of 1 by N. It is minus 1 by N square. That is the value. But it should be 0. By doing that one only, you get the value of N at which conductivity is minimum. Now, I am equating that one to 0. See, Q into mu N plus into minus minus Ni square into mu P by N square equals to 0. Here Q never equals to 0, then automatically remaining part should be equal to 0, this part. Therefore mu N minus Ni square into mu P by N square equal to 0. From this we can write N square is ni square into mu p by mu n. Therefore n equal to ni into square root of mu p by mu n. At this value, at value of n equals to ni into square root of mu p by mu n, your semiconductor conductivity is minimum. Once you know the n value, now go to the p value also. Now I am moving to, so we know this is the ni value we got, ni into root mu p by mu n, but we know p is equals to ni square by nn, ni square by nn. So ni square by n value, sorry, n is sufficient. Ni square by n is ni into square root of mu p by mu n, square root of mu p by mu n, which is ni into square root of mu n by mu p. So far you know the values of p and n and p at which your conductivity is minimum. So that means, therefore, at n equals to ni into square root of mu p by mu n and p equals to ni into square root of mu n by mu p, conductivity is minimum. Once you said it is minimum, just take the values of n and p, substitute in that equation. Our equation is q into n into mu n plus p into mu p, that is our expression. So just substitute the values in that. Okay, by substituting values in that, here I done already. Take that, this is ni into, it is a n value, ni into mu p by root mu p by mu n, and this is p value, ni into square root of mu n by mu p. Okay, in this expression I substituted the values of n and p. After simplification you get 2q ni into root mu n by mu n into mu p. That is the minimum conductivity, okay. And one more important point here is, now my question is, at a condition of minimum conductivity, listen carefully, I taken a semiconductor, this is semiconductor, just I know only one thing, that is, now your semiconductor possesses minimum conductivity. Now it gives minimum conductivity to you, it is giving. Now which type of semiconductor it is? Now is it an intrinsic semiconductor, n-type semiconductor, or p-type semiconductor, or n-type semiconductor with heavily doped, or n-type with lightly doped, or p-type with lightly doped, or p-type with heavily doped? Which type of semiconductor it is? Now just check the n and p value. Okay, see, if any carrier concentration is greater than ni, that they are the majority carriers, and if any carrier concentration is less than ni, that is the minority carrier. Based on the majority and minority carrier concentrations, you can say that given semiconductor is either n-type or p-type. Okay. Now, see this. See this, n is ni root mu n by mu p. We know one thing, mu n is greater than mu p. So once mu n is greater than mu p, from this we can write n is less than ni. So, and from this n is greater than, sorry, it is p is ni into root P is greater than, P is Ni into square root of mu n by mu p, but this is greater than 1. So P is just greater than Ni. Okay. See, compared to Ni, N value is less. That means electrons are minority charge carriers from this. I can conclude. Minority carriers. And from this, holes are majority carriers. Holes are majority carriers. Majority carriers. Electrons are minority charge carriers and holes are majority charge carriers. Now the semiconductor which gives these properties is p-type semiconductor. Now therefore it is a p-type semiconductor. In p-type semiconductor, okay, it is p-type, fine, but here P is majority carrier concentration is just greater than Ni, not that much. Okay, so it is a lightly doped p-type semiconductor. Lightly doped. P-type semiconductor. So far we know different points from this. At what values of N and P conductivity is minimum? And what is the minimum conductivity? Okay, now at the same time, what are the majority carriers and minority carriers, and at a condition of minimum conductivity, how that semiconductor behaves. We know all these things. Okay. Okay. So at a condition of minimum conductivity, your semiconductor behaves like a lightly doped p-type semiconductor. Lightly doped p-type semiconductor. Okay. So this is about our drift current density. Now we move to diffusion current density. See here, diffusion current density. Just before we discuss, whenever a concentration gradient, means change in concentration with respect to distance, exists in a semiconductor, at that time carriers are moving from high concentration region to low concentration region. Once carriers are moving from high concentration to low concentration, that movement is called diffusion movement, and that current is called diffusion current, and the density is current density, diffusion current density. Let us, I am taking this one on a plane. See, this is x-axis, and y-axis I am taking the hole concentration. Let us take hole concentration, and it is n-type semiconductor. By illuminating at one end with light, more number of holes are generated by breaking covalent bonds. This is the hole concentration here. This is the hole concentration under steady state here. At x1 P1, at x2 P2. Now here we can write concentration gradient is dP by dx, that is the concentration gradient. So you can write it as P2 minus P1 by x2 minus x1, or P1 minus P2 by x1 minus x2. Any one you can take, but finally you get it as a negative polarity, because if here P1 is more, okay, if once P1 is more, P1 minus P2 is positive, but x1 minus x2 is negative, because x1 is greater than x1. If you go back opposite direction, P2 minus P1 by x2 minus x1, here x2 is more compared to x1, but P1 is less compared to P1. That's it. Okay, this is concentration gradient. Now in this case, diffusion current density, J diffusion current density, J diffusion is directly proportional to concentration gradient dp by dx. Negative polarity you mentioned, so minus dp by dx, and at the same time it is directly proportional to charge of the hole. By combining those two, I am going to write, we can write J diffusion is directly proportional to minus q into dp by dx. Now I am adding a proportionality constant, that is a dp into q into dn by dx. Sorry, dp by dx, and this is negative. J diffusion, this is J diffusion by hole. So minus dp into q into dp by dx, this is the expression, and dp is called diffusion coefficient of holes or hole diffusion constant. Similarly, we can write for electrons also. Similarly, diffusion by electrons is dn into minus dn into q into dn by dx, but charge of the electron is negative, so minus dn into minus q into dn by dx. Charge of the electron is negative, sir, here, that's why I taken it as minus q. Now it became dn into q into dn by dx. That is the expression for diffusion current density by electron and hole. Okay, so already we derived all these things, and units for diffusion coefficient is centimeter square per second or meter square per second. Okay, so far we completed drift and diffusion phenomena. This drift and diffusion phenomena both are related by a relation, we called it Einstein relation. Einstein relation. Both drift phenomena and diffusion phenomena, these two are related by this expression. According to this, dp by mu p is dn by mu n is Vt, which is kT by Q. Vt is the thermal voltage, and its value is kT by Q. Now K we know, Boltzmann constant, Q charge. By substituting these values and simplifying, T by 11,600 you get. That is the thermal voltage. By substituting T 300 here, now you get, we check that value exact or not, that is 300 divided by 11,600. That is 0.02586. Okay, 862. So 25.86 millivolts. So practically we take it as approximately 26 millivolts. Approximately we are taking it as 26 millivolts. Now, so this is the final expression. You can write simply d by mu mod d by mu is Vt or kT by Q. In previous GATE examination, they asked a questions on this. That is, what are the units of d by mu? So we know the d value, units of d, centimeter square per second. Mobility units, we know that, centimeter square per volt to second. Just now centimeter square per second, centimeter square per second, it is volts. This is Vt, thermal voltage 26 millivolts. Milli is the value, so units are volts. kT by Q, units of kT by Q also volts. Now I want units of mu by d. D by mu is volts, mu by d is volt inverse. Similarly, I want the units of Q by kT. So kT by Q units are volts, Q by kT is volt inverse. So these are the units of d by mu, mu by d, like that. So this is the Einstein relation. Here just to we relate the drift and diffusion concepts. Those two concepts just to be related. Okay. Now during diffusion process, this is the diffusion process. Here more number of charge carriers. Next here is a less number of charge carriers. Now due to this concentration gradient, carriers are moving from diffusing from high concentration to low concentration. High concentration to low concentration. Okay. Once they are moving from high concentration to low concentration, what happens? During the diffusion, already these are the minority charge carriers. For example, if you are taking the n-type semiconductor, in n-type semiconductor, electrons are majority charge carriers. Plenty of electrons are available in this. Plenty of electrons are available because electrons are majority in n-type. Okay. But at one end, due to illuminated by light, at this end, electron-hole pairs are generated. Now these are the holes. When these holes are diffusing this side, this hole is going to recombine with this electron. Here recombine with this electron. Recombination is going on during this diffusion moment. Now some holes may be recombined by traveling this much distance. Some holes may be recombined here. By some holes may be recombined here. Some holes may be by traveling this much distance, they may be recombined here. Anyway, by moving away from it, hole concentration is decreasing exponentially with respect to distance x and with respect to time also. Okay, now here I am going to defining a parameter, diffusion length. The average length traveled by a charged particle during diffusion process. It is the average length traveled by a charged particle during the process of diffusion. That's it. Now it is represented by L. Diffusion length of electrons is Ln. Diffusion length of holes is represented by Lp. And for example, now I am taking the same thing. See, and one more thing I am going to giving one important point here. See this. In that semiconductor, under steady state, hole concentration is this one in n-type. Now by placing the light at one end, this much number of holes are generated at this end. These are the excess holes generated. Excess holes generated. Let us take it as P dash of 0 at this point. Now once this is n region. Now once this is happened, your holes are, because of here this is high concentration, low concentration, holes are moving this side. During that moment, holes are recombined with electrons, its concentration is decreasing, finally reach the steady state value. Now the expression for this one is only this one, sir. This part I am going to representing. Exponentially decreasing it is. So it is P dash of 0 into e power minus x by Lp. This is the expression for that. Okay, next. So far we know what is the diffusion length, and at the same time I want to give one more information, that is a lifetime, average lifetime of the charge particle. So that means once covalent bond is breaking, electron hole pair is generated. That means new carrier is generated. After some time they are going to be recombined by traveling some distance. By traveling some distance they are going to be recombined. Recombined here they are. Okay, now the average time lapse between generation and recombination is the average lifetime of the carrier. Okay, or the amount of time the carrier exists freely. Existing freely means it is generated before recombination, after generation and before recombination. That is represented by tau n. Now for electrons, average lifetime is tau n. Now for holes it is tau p. Holes it is tau p. And diffusion lengths are ln is represented by square root of dn into tau n, and for holes diffusion length is square root of dp into tau p. So my dear students, all these expressions are very important during solving the problems, and to understand the concept effectively you need to solve more number of problems on this. Don't forget, you need to solve more number of problems after thorough preparation of topic. Okay, so this is about your drift and diffusion current densities. Now you can take any semiconductor. In any semiconductor, total current density is J. Total is J current density by electrons plus current density by holes. Now in these two parts we have drift plus diffusion. J drift by electrons, and J diffusion by electrons. Similarly, in this also two parts, J drift by hole, and J diffusion by hole. So these are the two parts. This is the total current density in a semiconductor. Based on the situation, the respective value of current density we are going to be representing. Okay, so by solving multiple problems on this, you get clear picture on this also. This is the concept of drift and diffusion concepts. So next problems. So next session we go to the problems. Now I am thanking to one and all for spending your valuable time with me. Okay, don't forget to use my code during subscription VRAW10 to get 10% discount, and hit this bell icon to get the notifications. Don't forget to join our Telegram group to get the updates on our upcoming videos, and click on this subscribe button, and please give your valuable comments on YouTube to strengthen ourselves and to provide a better quality data, quality information to students. Okay, so now thanks to one and all. Once again I'm welcoming you all to India's largest online learning platform, Unacademy. Okay, so don't forget that outside situation is not good. That is not, so far it is not under our control. Okay, don't move freely, restrict your movement at your home itself, and whatever thing is happened at outside, our learning process should be continue. It cannot stop. So for that, join our Unacademy. Stay at home, stay safely, but you continue your learning process by staying at your home itself. Okay, thank you, and thanking to one and all for your